Okay, today we're going to draw some Lewis dot structures. We're going to learn a little bit about resonance, a little bit about formal charge. Some of this might be, actually a good bit of it might be review for you. We're just going to go in a little more detail than you did last year. So I'll let you read that on your own, but Lewis dot structures are a way to two-dimensionally study what a molecule looks like with its geometry. And once we know its geometry, then we know we can predict a lot of things about the properties of that molecule. So I'll also let you look at that on your own, but that just gives you like a step-by-step account of how we're going to go about drawing these Lewis dot structures. But basically we're going to use valence electrons, and we're going to distribute those valence electrons wherever we feel that they should belong, so that everything has a outer valence shell that's full. So for hydrogen, that's going to be the duet role, 2 electrons. For all the other atoms, it's going to be 8 electrons. Okay. This is going to be of interest. I don't know how many of these you guys did last year, but if you would work on any Lewis dot structures that are not atoms, if they're ions, you have to designate that they're ions. And so we're going to have the molecule, well, not the molecule, but the polyatomic ion inside these brackets, and then whatever charge that ion has outside. And that is going to designate that we have some electrons that we accounted for. So if it's a -2, that means it's gained 2 electrons, and we have 2 more electrons that we have to use. Okay, and we're not going to give any ownership of these electrons once we do the Lewis dot structure. It's a very simplistic method. So these electrons that from all the different atoms involved, those valence electrons, we're just going to distribute them wherever we feel they need to be distributed. So here's some examples, and you can use all dots if you'd prefer. You could use a combination of dots and lines, but you definitely need to use dots if they're unshared electrons. Okay, and on top of that, because you might have lots of dots, it's a good habit to get into. Now, these are all printed out, so it wasn't needed here, but it is suggested that if you have any unshared electrons that are around the central atom, and nitrogen and oxygen are central atoms in these 2 cases, that I circled those, and that way they don't get lost. And later on, we're going to find out that these electrons here are going to play a significant role on the geometries of those molecules. Okay, I'm not going to be able to, for time constraints, I'm not going to go through and do every one of these. You should practice these. You can look on you can Google the Lewis dot structures of these after you attempt them. But I'm going to show you the way I would go about doing them for the first time. So let's do carbon with 2 oxygens, carbon dioxide. So the least electronegative atom is always going to be in the middle. And if you're not sure, oxygen is typically not going to be in the middle. Carbon is always going to be in the middle. Okay, if the molecule has carbon in it, it's going to be in the middle. So that we could call that a skeleton structure there. Then somewhere I'm going to, either in my head or actually write it down. In this case, I'll write it down. How many valence electrons do the atoms possess? And if you just count the column, whatever column it's in, that's going to give you the valence electrons. Carbon's in the 4th column, so it has 4 valence electrons. Oxygen is in the 6th column. Again, we're skipping the noble gas. The transition metals. We've been doing that. If we skip those, it's in the 6th column. So each oxygen has 6. There's 2 oxygens for a total of 12. Add those up. That's 16 electrons. So what I would do first is try to distribute 8 electrons around every atom. and see what happens. So I think you were, the first time you did these, your teacher may have done this for you. And two things have to happen. One, everything has to have 8 electrons around it. Yes. So that looks like success. And by the way, we're borrowing a little bit from Venn diagrams where the circles interact. There's some dots, and that just means that those electrons are being shared between the two atoms. So we got half of it done. Now, did we distribute 16 dots? And if I count these up, I'm starting left to right, but I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh, way too many dots. So what does that mean? That's not the Lewis dot structure of carbon dioxide. So I'm going to have to go back to the drawing board. I'm not going to go and change my well, I guess I did. I didn't really want to change my skeleton diagram. I just accidentally erased 2 of the atoms there. But so I still have my carbon, my 2 oxygens, but I need to come up with another way to get 16 dots so that everything has 8 around it. So the next thing we could do is try, instead of 2 dots between atoms, we could do 2 pairs, total of 4. So that's a double, that signifies a double bond. So now if I would draw a circle around carbon, there's 8 dots already there. No more dots for carbon. But I think we have to have some more dots, more electrons for the other atoms. So if I draw now, and I wouldn't do this for each one, but the first time I'm trying to explain this to you guys, I'll use these circles. But I think you'll quickly stop using those. So if I put those circles around oxygen and carbon and oxygen, I get some overlap, and that signifies 4 electrons between each of the carbon and oxygen. That's a double bond. And then I counted these up, 2, 4, 6, 8, 10, 12, 14, 16. I got my 16 dots, and everything has 8 around it. So that is the correct Lewis dot structure. To clean this up a little bit, let's go and just redo. Whoops. If you don't like that, you could go like that. Okay, both those are equally correct. I'll probably do one of each of these slides here. But that's the method I would use. Try single bonds first. If that doesn't work, then go doubles. If doubles don't work, try triples. If triples don't work, then you did something wrong. Okay, so now let's go a little more complicated here. Let's do HNO3. So H, by the way, hydrogen, it has 1s1. It has 1 electron in that orbital there. It needs 1 more. Not more than 1, 1. So what does that really mean? Hydrogen can never be inside of the molecule. It's going to have to be around the fringe, around the edge. Nitrogen, compared to oxygen, is a lower electronegativity, so it's going to be the middle. And we would have to have an oxygen. We'd have to have an oxygen. We'd have to have an oxygen. And you don't know this. That's why I'm going to tell you that when you have this type of molecule and the H is in the front, that's an acid. And acids are always going to have this look. Okay? So there's a couple memorization things you're going to need, and that's one of them. So now we have to figure out how many dots do we have and how do we distribute them. So hydrogen is in the first column, so that's 1 electron. Nitrogen's in the 5th column, so that's 5. And then oxygen is in the 6th column, That's 6 electrons, but there's 3 of them. That's 18. Let's count all those up. And that looks like we got a total of 24 dots. So I think I had mentioned to you that the first thing I would try to do is go single bonds everywhere and everything having 8 around it. Well, except hydrogen only needs to have 2 around it. Whoops, that's not a very good last dot there. Okay, so everything has 8 around it, but did we use 24 dots? I'm going to count 8 at a time, I think. There's 8. There's 8. There's 8. That's 24. Uh-oh, 2 more. We have 26. So that is not correct. So if single bonds don't work, that means that we might want to try a double bond. Let's give that a shot. Now, with that last one, I just jumped right to 2 double bonds. I really probably should have went 1 single bond first. I've done carbon dioxide many times, so I knew it was going to have 2 just to save us a little bit of time. It's not a very good option there. Let's make that a little smaller. Okay, so let's try just a single bond with all the locations except for 1 double bond. And it doesn't really matter right now where we're going to put the double bond. It has to be between a nitrogen and an oxygen. That's true. Okay, so let's go and let's make sure everything has 8 around it. The nitrogen already has 8 around it if you count all those 8 dots. And then we need 4 more here. So did we use the correct number of dots this time? Well, let's see. There's 8. There's 8. There's 8. And the nitrogen has 8. And remember, hydrogen only has 2. So everything has the right numbers. Did we use 24 dots? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Bingo. That is correct. Okay, so that's the rule for that. Maybe we better do one more of these because we didn't do a polyatomic ion yet. We'll do this bottom one here. So 2 atoms, so there can't be really an atom in the middle. And what do we got here? Carbon has 4 electrons. Nitrogen has 5 electrons. Oh, but we have this charge. That means we have a -1 charge. That means 1 more electron. So we have a total of 10 dots. So you could try single bond. That's not going to work for you. You could try double bond, and that's not going to work for you. I'm going to go straight to a triple bond. And again, you could use the lines. I used the dots here. And I just drew 10 dots. 2, 4, 6, 8, 10. The carbon has 8 around it. The nitrogen has 8 around it. That's good. Oh, not quite good. You need the brackets and you need the charge. Now that is good. It is so easy to forget that, and it sounds like that's nitpicky, and it is nitpicky, but it's very important. And you'll definitely have at least one of those polyatomic ions on the test. Okay, so while we were drawing these, you may have thought to yourself, wait a minute, I think I could have drawn it this way and it would have satisfied your rules, Mr. McNally. I would have had 8, the full octet or the full duet if it was hydrogen, and I would have distributed the right number of dots and everything would have been fine, but it wasn't what you had. And sometimes that's the case. And to break that tie, we're going to use something called, formal charge. So there are times where this very, very easy method, this Lewis dot structure method, sometimes can get different answers that look like they're correct. But that doesn't mean that they're the ones that are going to be out there in nature. So to figure out which one is more liable to really occur, we have to do this thing called formal charge. And there's a little equation for formal charge. And this equation is not provided for you, so you're going to have to memorize that. So you're going to count up the valence electrons for a particular atom that's in the molecule, and then subtract any lone electrons, that's the ones that aren't being shared, and then you also subtract half of the shared. Okay? And you'll designate each atom in the molecule with a certain formal charge. And you'll look at all the formal charge atoms that are in that molecule, and you can kind of add them up if you want to, or just look at them compared to the other structures that you might draw. And the more zeros, the closer you are to zero, the better. Okay? And that may not make a lot of sense till we try one of these. Which Lewis dot diagram is correct? So, by the way, it doesn't look like these have all the dots here. So remember that everything has to have 8 dots around it. So they didn't draw these dots. Okay, so again, you have to look at nitrogen, you have to look at carbon, you have to look at sulfur with each of these. So here's the nitrogen. It has 5 valence electrons. It's in the 5th column. You have to subtract all the unshared. Looks like there's 4 unshared. And then you have to subtract half of the shared. Well, remember, a line is 2 dots. So there's 4 dots there, so half of that is 2. So that would give you a -1. We would love a 0. -1's not as good as a 0. Carbon, 4 valence electrons, no unshared, and half of the shared. Remember, each line is 2 dots, so it actually has 8 dots that are being shared, electrons that are being shared, so half of that is 4, so that looks 0. Oh, we like 0. Sulfur is in the 6th column, 6 valence electrons. It has 4 unshared, and half of the shared is 2. That equals 0. Okay, that's not bad. So the only thing that could beat this out is if it's 0, 0, 0. So let's check out this one, the second one here. Carbon, for this one, 4 valence electrons, 4 unshared. That's going to give you a -2 there. Nitrogen, 5 valence electrons, has no unshared. Half of the shared gives you a +1. I can tell you right now, without even doing the sulfur, this isn't looking too good. Again, we like that we would have the most zeros. Sulfur, 6th column. It has 4 that are unshared, half of the shared, so that is a 0. But of these 2 that we've done, we like this one better. It has a -1, a 0, and a 0. The bottom one here, carbon, 4 valence electrons, 4 unshared, half of the shared, that's a -2. The sulfur, 6 minus 0, -4, that's not looking too good. Nitrogen is 5 valence electrons, 4 unshared, half of the shared. That gives you a -1. This one's like a disaster. Not a disaster, but it's definitely not correct. Of the 3, this is the best bet. Would we have preferred a 0, 0, 0? Yep. Did it exist? No. So of these 3, that's the correct one. Okay, so you're going to have to practice formal charge a few times like I just did there to understand which of these molecules we would like. Let's check out one of these. Draw the most likely Lewis structure for the following. I think that's a misprint there. That's supposed to have an N in that. Remember I said carbon's going to be in the middle. You could probably come up with a number of different ways that you could start this out. I earlier had done this, and I think we're supposed to have 2 dots there, and we're supposed to have 2 dots there. Another way you could have drawn this would have been, I'm going to draw it way up here. You could probably come up with more ways than this too. Okay, so both those have the exact same number of dots, same number of atoms, everything has 8 dots around it, but one of these is more likely to be found in nature than the other. How do we break the tie? Formal charge. Now, you could look at all the nitrogens, all the carbons, all the hydrogens, and sort them out. But you'll never have to look at the hydrogens. Why? Because hydrogen, no matter what molecule it's with, it always bonds identically. So it's always going to give you the exact same formal charge. So don't bother looking at the hydrogens because they're going to give you the same values with every compound you'd ever do. But look, we'll look at the this nitrogen. By the way, it's going to be different than that nitrogen. This one has 5 valence electrons. It has 2 unshared, and half of the shared give you that. Let's look at the other. Well, we'll look at carbon next. We'll just go left to right. Carbon has 4 valence electrons, no unshared, half of the shared give you a 0. We're liking this one already. This other nitrogen, this is the one to the right, 5 valence electrons, 2 unshared, half of the shared, that's 3. Oh, we can't beat that one. Can't get better than 0, 0, 0. But we'll check out this one too. Remember I said don't bother with hydrogens because they're always going to give you the exact same value. So this first nitrogen on the left side, 5 minus 2 minus 3. Oh, we like 0. We like 0. Carbon, 4 minus 0 minus 4. Oh, this is looking really nice here too. Nitrogen. We got 5 minus 2 minus 3. Guess what? They both are winners. That occasionally occurs. By the way, you probably could have come up with many different ways to put the carbons, hydrogens, and nitrogens together that would not have been either of these two structures. Those likely would not have formal charges that would be 0, 0, 0 like this is. So what does that mean? That means they're both right. And that's going to give us our next vocab, resonance. It resonates between, if you see here, well, actually we're not going to quite use this example for resonance, but it does mean that both of these are both found in nature. So if you did either of these two, I wouldn't have this one on the test because we like on the test one particular right answer, not multiple right answers, but both these would be found in nature. Okay, at least from formal charge. Okay, so someone maybe was told to draw the Lewis dot structure of carbonate, and a couple of people drew it this way, but then a couple of their buddies did it that way, and then a couple of their other friends did it this way, and then they start arguing which one's right, and they all do the formal charge, and they all get the identical same formal charges. So what does that mean? That means that they're all right, and we're going to now use this term, resonance. This double bond resonates between this single bond spot and this single bond spot. So if you took a snapshot, you can't really take a snapshot, but if you took a snapshot, you might get that, you might get this, or you might get this. It resonates between those three. So what does that really mean? It really means that this is not really a double bond. That means that this really is not a single bond, and that means this really is not a single bond. There's really 1, 2, 3, 4 lines there, and there's 3 connections. So really, they are a 4/3, which nobody says that. But many people say that this carbon auction or this carbon auction or this carbon auction, any of the 3 carbon auctions there, have a bond order of 1 1/3. So again, what we did was we took all the lines, the connections, the bonds, and we divided it by the number of places that those connect. And that's how we got that bond order. So it's a 1 1/3. That means that it's not quite a 1, not a single, not quite a double. So remember, single bonds are the longest, double bonds are a little shorter, and then triple bonds are the shortest. So this is 1 1/3 is going to be somewhere in between the single bond length and the double bond length. So we can give this one a shot. Nitrogen with nitrogen and oxygen. So 5 electrons plus 5 electrons plus 6 electrons. That gives us 16 dots. Okay, so we're not going to want to, but we could try this first, and I know this is not going to work. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whew, way too many, way too many. So maybe we got to go back to the drawing board. So maybe you could go, let's give this a shot. What would happen if we did that? 2, 4, 6, 8, 10, 12, 14, 16. Bingo. That looks like that works. Could we go that? 2, 4, 6, 8, 10, 12, 14, 16. That also has 16 dots and everything has 8 around it. Could we also have gone 2, 4, 6, 8, 10, 12, 14, 16. What? 2, 4, 6, 8, 10, 12, 14, 16 dots. Yep. So you could go look at the Lewis dot structures of those. If they have the same, you go through the formal charge of all 3 of those. If they have similar outcomes for formal charge, then it resonates between those type of bonds. Okay. So here's a couple more resonance structures. Oops. This is a good habit to get into. Just make sure you do the brackets with the minus before you even get anywhere, because you might forget to do that later on. Nitrogen has 5. 3 times 6, 18. And then this negative means it has 1 more electron. So that looks like you have 24 dots. Since it's going to be resonance, we know it's not going to be single, single, single everywhere. You can't resonate between all singles. So let's try this first, and let's see if that gets us anywhere. So we're only allowed to use 24 dots. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 dots. Guess what? That's right. So a lot of people use this double arrow routine here, and you could put the double bond. I'm just going to kind of like shorten this up a little bit so I can write this quicker, and then I could go another double arrow there and do another one. And then this time the double bond is over here. Okay, now I didn't finish those 2, but it resonates between those 3. And then benzene was that special one. I'm not going to go through the details of that, but benzene has to have, it's that aromatic structure 4, 5, 6. So if these are all going to be hydrogens off of here. You have to make this happen. And so the double bonds can resonate between the double bond spots and the single bond spots. And lastly, you didn't do any of this in first year chem. There are exceptions. How do we know these exceptions exist? Because we know these molecules exist. So the Lewis dot structures are very, very, very simplistic, and they work for lots of things, but they don't work for everything. And so there's some molecules that just have not enough electrons around them, like BF3. BF3, boron is 3 electrons. Fluorine is 7 times 3, 21, for a total of 24 electrons. So it looks like there's fluorine. So there's 24 dots. It doesn't appear, no matter how you want to do this, there's no way that you're going to be able to get boron to have enough electrons. Okay? So that's just the breaks. That's how it is. So BF3 is going to search out something that it can share 2 more electrons with. Ammonia happens to be a terrific one. Here's ammonia. And those 2 electrons are going to get shared with boron right in that location. And you can write it a bunch of different ways, but a lot of people write it that way. And this is outside the curriculum, but in case you were wondering, this is called a coordinate covalent bond. Okay, and later on we'll figure out that this is a base. Oh, it says right there. And this is an acid. Not certainly the acids you're familiar with, but it's an acid. And you can have a couple other exceptions. So we had exceptions where it didn't have enough. By the way, any of these exceptions are going to be located around the central atom. Sometimes you just can't add up enough electrons to get you a even number. And everything we've done so far had been an even number. Well, that's not going to be the case here. So nitrogen's in the 5th column and oxygen's in the 6th column. That's 11 dots. That's not going to cut it. So something is going to be shortchanged. So what's going to be shortchanged? Well, it's not going to be oxygen. Oxygen has a higher electronegativity value, so it's going to attract electrons more than nitrogen. So nitrogen is going to be shortchanged. It's not going to. It's not going to work out for nitrogen here. So we have 11 dots. We could try this first, and I know this is not going to work. 2, 4, 6, 8, 10, 12, 14. That's way too many. I'm only allowed to use 11. So if a single bond doesn't work, what do? We double them up. We do a double bond. So now let's go 2, 4, 6, 8, 10, 12. I'm only allowed to use 11. So here's our short change. Nitrogen just doesn't get enough. So is that a stable molecule? No, it is not. It's far from a stable molecule. It's ridiculously reactive. And if that reacts in your body, cell damage. So if you were unfortunate enough to breathe, to get some free, by the way, they call them free radicals. If you get free radicals, which unfortunately we all do, it's going to try to react with whatever it has a chance to react with. So that could cause damage. It could cause the cell to die. It could even cause cancer. So it could damage your DNA. And then our last type of exception is expanded octets. These are atoms that are going to have too many. So this is a strange one because I don't think you guys have ever done any noble gases. But as you get further down the periodic table, those outer electrons are so far away from the nucleus that we can get them, some of those, to actually react and form compounds. So let's do this one. So xenon is in the 8th column, and then chlorine is in the 7th, but there are a bunch of those. There's 4 of them, so that's a total of 28 electrons with all the chlorines. So that's 36 electrons. That's a lot. So how Halogens also are going to be always on the outside looking in. Xenon's going to be in the middle. And then let's put, I haven't used any lines yet. Let's use a line here. So line signifies 2 dots, remember. So then these chlorines have to have 8 around them. So let's do that. So if I do that, that only gets me to 32 dots. You can count them up, but you're going to get 32 dots. So remember, line is 2 dots. I'm supposed to have 36. Does that mean I screwed up? Nope. That means that xenon is an expanded octet, meaning that it has other locations that it can share electrons in. And how is that possible? Well, as you go down the periodic table, you start to enter into the areas where the S's and the P's and the D's, those orbitals are open to the ability to be valence. And so that's how this one works. So xenon has, let's go with different color here. It has 2, 4, 6, 8 electrons that are bonded, or shared, I should say. And then 2 sets, 4 electrons that are not being shared. And that's going to give it a very special property compared to another molecule that you probably had done last year. I'm not putting all the outside electrons in there, but carbon has the same type of bonds off the atom, but it has the lack of those extra unshared electrons that xenon has, and that's going to give it a much different shape, and that's going to give it different properties. And so there's a few more here you can practice. And again, you have the opportunity to go on to Google afterwards and check your answers. And you can also ask me any questions about any of those ones that we didn't get to.